What makes a good diagram? As mathematicians, we love diagrams. They're often the key to understanding complex relationships. The Pythagorean theorem, an equation with context, or bam, diagram. De Morgan's law in propositional logic, this weird rearrangement of symbols, or bam, a nice clean Venn diagram that sums up the relationship. Are these two variables correlated? I don't know, we could crunch through the numbers, or bam, clearly there is some correlation. Diagrams are often the first thing I deploy when trying to solve or explain a problem, as I did extensively in my last video. So good diagrams provide clarity, but great diagrams, they go further. Some diagrams are so great that they lead to the development of new theory. I'm talking about diagrams like this. So what is it? Well, there's a complicated mathematical structure out there that's difficult to visualize and work with, but this one structure connects coding theory, group theory, sphere packing, combinatorics, and much, much more. And this diagram was so effective that it allowed mathematicians to reinvigorate their study of it. That's what we'll go into in this video. What is this mysterious structure? What is its connection to so many disparate areas of mathematics? And how did this diagram provide a much needed window into its properties? And it really is amazing. It's no wonder at all why the author who first conceived this diagram described it as nothing short of a miracle. Just want to let you know that there are always bits and pieces that crop up in my research that are interesting but don't feed directly into the main video. You'll find some of those in an extended cut of this video available to my patrons as a thank you for all of their generous support. My patrons also get early access to my videos, we hang out on our dedicated Discord server, they see behind the scenes updates, and they get to see some silly bloopers. If any of that interests you, or if you just want to support me, please consider doing so on Patreon. I'd really appreciate it. Also, while I'm self-promoting, I recently started streaming on Twitch. Lately I completed a Steel Soul run of Hollow Knight and started a run of Blasphemous and plan to play many other Metroidvania and puzzle games over there, so if that's your thing, come and join me. I always love to interact with viewers. Also, I'm planning to do my annual Maths Marathon charity livestream where I complete 24 maths exams in 24 hours on the weekend of the 8th of July, so I hope you can join for that. Anyway, video. First, I'm going to start with some motivation. If you're anything like me, a pure mathematician, then the structures that we'll be looking at will be interesting enough in their own right. But I hear that some people out there actually care about how the mathematics is applied. I joke, but this next very brief section is for those people, and it does introduce some important concepts that we'll need going forward. Let's say I want to transmit a message. The message will be yes or no, where 1 is yes and 0 is no. So I'm sending one binary digit, or bit. The problem is that every medium of transmission suffers from what we call noise. Interference that can change the bit during transmission. Let's say, for example, that there's a 10% chance that the bit changes during transmission. Then if I receive a 1, there's a 90% chance that his answer is actually 1. Not bad, but what if I'm answering a vitally important question like, should I subscribe to your YouTube channel? I want him to be very confident in the answer. My channel is better. I told you to stick to the script. If I can't fix the noise, how do I increase the likelihood that the correct message is received? Well, now imagine that I have 2 bits, where 1 is yes and 0 is no. Both bits still have a 10% chance of changing during transmission. But now, if I receive 01, then I know an error has occurred, because 01 isn't a valid code word. But it's just as likely that he meant 11 and the first bit has changed, or he meant 00 and the second bit has changed. In other words, he detected an error but was unable to correct it. This is called an error detecting code. But now add a third bit, where 111 means yes and 000 means no. Then if I receive 010, I know he probably meant 000. He is able to correct the error to the most probable valid code word. So this is called an error correcting code. That is, assuming some basic competence at the other end. That was uncalled for. What's going on here numerically that makes this third code error correcting? You can go now. Can't I stay? Let me put it this way. Error correction has to do with the distance between the code words. Distance here is just how many digits do you need to change to get from one to the other. This in coding theory is called Hamming distance, but I'm just going to call it distance for now. For example, 0, 1, 1 and 1, 0, 1 are distance 2 away from each other because I have to change 2 of the digits. Now we already know that error detection occurs when our received message isn't a valid code word, but error correction occurs when we can map the received message onto the valid code word the shortest distance away. For example, earlier these were my two valid code words and yellow Alex received 0, 1, 0. That's a distance 1 away from 0, 0, 0 and distance 2 away from 1, 1, 1. So he corrects it to the code word shortest distance away, which is 0, 0, 0. It turns out that the distance between the valid code words is really important for error correction. Think about it this way. This graph will represent the whole possibility space, every string of 3 binary digits. I'm going to draw an edge between them if they are distance 1 away from each other. In this way, we can see that any erroneous message is distance 1 away from one of the valid code words and distance 2 away from the other, so we can always decode it reliably into a valid code word. I'm not going to get into the full details here, but it essentially comes down to drawing a sphere around each valid code word, and then everything in a code word's sphere is decoded to it. Because the code words are sufficiently far away, we can draw these spheres in such a way that they cover the whole possibility space without overlapping. If we try to do this for the 2-bit case, we can see that the spheres do overlap, which is why this code isn't error correcting, because this received message is in both spheres, which means it doesn't have a reliable valid code word to be corrected to. So the punchline is this: to make error correcting codes, we want to find valid code words that are spread out, to create possibility spaces that don't overlap very much. And we don't just want codes that have yes and no. What if we have a whole list of words that we want to encode, send, and then potentially get corrected on the other end? So if you take nothing else away from this section, it's this: there is value in finding sets of things that don't overlap very much. Let's examine a way to formalize that notion and produce, in my mind, some of the most beautiful and fascinating combinatorial structures yet discovered. This mysterious object I alluded to earlier is something called a Steiner system, named after Swiss geometer Jakob Steiner, who was once described as a middle-aged man of stout proportions with a long, intellectual face. And intellectual, yeah, let's go with that. So what is a Steiner system? Well, they are a type of block design, basically a collection of subsets of a set satisfying certain properties. Depending on the properties you stipulate, you get all sorts of different structures with different applications. Here's the property that defines a Steiner system. We have 3 parameters t, k, and n, and t is less than k, which is less than n, and we call a Steiner system STKN. N is the number of elements in our overall big set. We usually call this big set omega, and for simplicity, just let it be the set of integers from 1 to n. We're going to be building a collection of subsets of omega, and these subsets we call blocks. K is the number of elements in each block. Now here's the key property that makes this a Steiner system. Every subset of omega that contains t elements must be contained in exactly one block. And it seemed so simple, didn't it? Well, don't worry, it is. This definition is a bit of a headache, so let's look at an example. So let's look at S237. Remember, 7 is the amount of numbers that we have to play with, so omega is the set of integers from 1 to 7. And we're going to build subsets, or blocks of omega, of size 3. Let's just write down some 3 subsets. But the rule is, if I pick any 2 elements from omega, they have to live in exactly one block. And we can see here that I've broken the rule, because the pair 1, 3 lives in 2 blocks, which is forbidden. I've also broken the rule another way, because the pair 1, 4 doesn't live anywhere. So every pair needs to live in one block, and only one block. So this is a failure. Let's give it another go. So let's do this properly. Each column is going to represent a block, so every column will contain 3 numbers. Let's start with the first column, and let's just think about the pair 1, 2. Well, that has to live inside some block, so let's just assume that it's the block 1, 2, 3. And now we think about 1, 4. Now the pair 1, 4 has to live inside some block, I can't fill this block up with 2 or 3 because then the pair 1, 2 or 1, 3 would live inside 2 blocks, which is forbidden. So let's just assume it's 1, 4, 5. Then apply similar reasoning for the pair 1, 6 and block them up with 7. Now a couple of observations. Note that none of these blocks can contain a 1. If it did, then it would have to be paired with another number, but then that would repeat the pair in a previous block, which is forbidden. And also note that there's nothing special about 1. Since we've realized that 1 appears in exactly 3 blocks, that must be true of all the other elements as well. So we're looking for 2 more blocks that contain 2, 3, and so on. Now, 2 so far has never been paired with 4. And now to complete this block, well, we can't complete it with 3 or 1 because 2 has already been paired with 1 and 3. We also can't complete it with 5 because 4 has already been paired with 5. So let's just assume it's 6. And then observe that 2 has never yet been paired with 5. And since 2 has never been paired with 7 and 5 has never been paired with 7, we can put a 7 here. Now consider the number 3. There needs to be 3 blocks that contain the number 3. So far we only have 1. So these 2 blocks must contain 3. 3 has never yet been paired with 4. Now to complete this block, note that 4 has already been paired with 5, 4 has already been paired with 6, so we must have to pair it with 7. And then finally, 3 has never yet been paired with 5. And we note that 3 has never yet been paired with 6, neither has 5, so we can complete it with 6. And that, my friends, is the Steiner system S237. Now, pretty cool, but this is just a jumble of sets. Let me draw you an amazing way to visualize this that just makes this, just all clicks together so nicely. Here, every point represents one of our numbers, and I'm going to draw a line through 3 numbers when there is a block that contains those 3. And it has the property that any 2 points defines a unique line. So every line will contain 3 points, and every pair of numbers is only going to belong to 1 line. So the pair 3, 5 needs to define a line, and we complete it with 6. 1, 7 needs to define a line, and we'll complete that with 6 as well. And then we also have this. We have that 2 and 4 define a line. We complete that with 6. 3 and 4 define a line. We complete that with 7. 1 and 5 define a line. We complete that with 4. And then this looks complete, except also 2 and 7 need to define a line. And if we look at our chart, 2, 7, and 5 define a line, which are these points here. And what I do is I complete this with a circular line. And this basically encodes the whole thing. So for example, the line 3, 4, 7 is this set here, 3, 4, 7. And just look at how much more pleasing this is to the eye. The power of a good diagram. Now, this is cool and everything, but it quickly gets messy. Try deriving the Steiner system S2313 yourself, and you'll quickly run into trouble. If you try and do it the naive way like this, if you're not careful, you quickly run into problems like blocking yourself off from completing blocks. So like I did here, for example, 3 and 4, I said, well, 4 has never been paired with 7 and 3 has never been paired with 7, so I can just stick a 7 there. That was fine in this case, but if you do it for the 13 case, what you end up with is you have to write a 7 there, yet 7 has already been kind of taken up by the previous block, so you have to do it a bit more carefully. With a bit of work, you can derive S2313, but you can appreciate that these very quickly turn into non-trivial structures to derive. In fact, for all choices of t, k, and n, there are surprisingly few valid Steiner systems, and some choices of t, k, and n where the existence of a Steiner system is still an open question. Just to build your intuition, I'm going to very quickly derive a Steiner system where t and k are a little bit bigger, like in S348. I highly encourage you to get some pen and paper out and have a go at this yourself, because this one is very doable, and it's interesting to see how the blocks sort of behave when these parameters are a little bit bigger. I'm also going to use this notation here, putting a cross in each row when I take that object into the block. So for example, this column represents the block of integers 1, 2, 3, 4. I can do this because the choice of object is pretty arbitrary. By convention, we usually set it to be the set of integers from 1 to 8, but I could choose any 8 objects here and still get a valid Steiner system. Again, I highly encourage you to give this one a go on your own, because I'm going to go through the solution pretty quickly now. Start by considering all triples that contain 1, 2. So 1, 2, 3, 1, 2, 4, 1, 2, 5, and then 1, 2, 6. Then the only ones left are 1, 2, 7, and 1, 2, 8. Now we convince ourselves that the pair 1, 2 will never appear in another block, and because it isn't special, and because it has appeared in exactly 3 blocks, every pair will appear in exactly 3 blocks. So the next pair to consider will be 1, 3. 134 has already gone, so let's consider 135 and 136. Because 178 has already appeared, I couldn't have 178 in either of these blocks, so I had to split the 7 and 8 up. Then it's going to be a very similar process with the pair 1, 4. We need exactly 3 blocks containing 1, 4, and then we fill them up the only way we can. At this stage, you should convince yourself that 1 will never appear in another block, and therefore, because 1 isn't special, since it has appeared in 7 blocks, every element will appear in exactly 7 blocks. So therefore, we need 4 more blocks containing 2. The pair 2, 3 and the pair 2, 4, they've only appeared once, so we're going to need 2 more blocks containing those. And following a very similar process, you fill them up basically the only way that you can. Now, so far we've got 5 3s, so there's going to be 2 more blocks containing 3. And the pair 3, 4 has only appeared once, so both of these blocks have to contain 3, 4. And then again, our hand is forced in how we fill those up. And now looking across, 1, 2, 3, 4 have appeared in 7 blocks each, whereas 5, 6, 7, 8 have only appeared in 6. So the last block has to look like this. And there we have it. Now, I actually knew a few things in advance that helped me to derive this system. Like, for example, I knew that it exists. Always helpful to know before you attempt a derivation. The other thing I knew, for example, was that there are going to be 14 blocks in the whole system. How did I know these things? Well, they're in my script, but how did past Alex know them, who wrote the script? Let's address the number of blocks first. So how do we calculate the number of blocks? Well, the way to do it is to count the total number of triples that are contained in here. So the first way to calculate the number of triples is to say, well, we've got 8 elements, and how many ways are there of choosing 3 of them? Well, that's just 8 choose 3. But there's another way to count them. Let's say that I have B blocks, and now for any particular block, there are 4 choose 3 triples. And note that because this is a Steiner system, every triple appears in exactly 1 block. So if we take the number of blocks multiplied by 4 choose 3, that is exactly the number of triples. Since these have both counted the same thing, they must be equal to each other. And now we can divide both sides by 4 choose 3, and that gives us the number of blocks. And there was nothing special about my choice of 3, 4, and 8. So in general, this is n choose t over k choose t. This is good. Whatever we choose for our parameters, we know that we're looking for that number of blocks. This helps with the existence question as well, because if this is not an integer, then the Steiner system cannot possibly exist, because we have to have an integer number of blocks. Note that this being an integer is a necessary condition, but not a sufficient one. So for example, there are parameters tk and n for which this is an integer, yet the Steiner system on those parameters does not exist. For example, S2, 3, 10, if we do n choose t, that's 10 choose 2, we get 45. And if we do k choose t, which is 3 choose 2, that's 3. 45 divided by 3 is 15, which is, trust me, an integer, yet this Steiner system does not exist. Why not? Well, I'll leave that as an exercise to the viewer, and I'll leave a hint down in the description if you need it. So that should give you a flavor of Steiner systems. Soon, we'll turn our attention to one specific Steiner system, which is a bit of a celebrity in the world of mathematics because of its incredible properties and underlying structure. First though, there are 3 questions we want to ask about Steiner systems in general. It is these questions that drive the connection between Steiner systems and many of these other areas of mathematics we alluded to earlier. So let's quickly run through those. Question 1 is this. Given a T set, how quickly can we find the unique block that contains that set? And no, I know I'm British, but not that kind of T set. Let's revisit our old friend S237. What we mean is if I give you a pair of numbers, how quickly can you find the block that contains 4, 7? Remember, the blocks follow this Highlander property. There can be only one. So how quickly can we find the unique block that contains 4 and 7? That's the beauty of diagrams like this. This shape, by the way, is called the Fano plane, named after mathematician Gino Fano. And I know what you're thinking. You're wondering, how stout was his figure? How long and intellectual was his face? Well, strangely enough, I couldn't find anyone making any such remarks about him. So we'll just have to judge for ourselves. Anyway, in the Fano plane, if you give me 4 and 7, I just highlight those, and the unique line that they create completes the block with 3, which is exactly what I found there, but this is just way prettier. And imagine more complicated Steiner systems where there are way more blocks than this. This is where good diagrams really come into their own. And that's all I'm going to say about this for now, just that we are very interested in the problem of given T elements, find the unique K block that contains them. We are very interested in this problem. Now, you might rightly ask why we care about that problem. Well, the pure answer is that that's the property that defines a Steiner system. Given a T-set, there's a unique K-block that contains it. So the more we know about that question, the more we understand about Steiner systems in general. The applied answer to this question might be something like this. It links back to the error-correcting property that we spoke about earlier. If this is in some way your code, and your received message is 47, you want to be able to quickly correct it to the closest valid code word, which is this unique K block. So this in some sense links back to that error correcting property we spoke about earlier. My next question is, if a Steiner system exists, is it unique? And what do I mean by that? Well, let's revisit S237 again. Earlier, I managed to derive this Steiner system, but take a look over here. Here, we have a collection of 3 blocks that follow the Steiner system property. If you pick any 2 numbers from 1 to 7, they appear in exactly one of these blocks. So this is a valid alternate version of S237. We can clearly see that it's different because it contains this one, 567, which is nowhere to be seen over here. So it is distinct. However, there is a sense in which these 2 Steiner systems are actually the same. And what I mean is, I can actually relabel the objects in here in such a way that I derive this one. So for example, if I swap all the 1s for 6s, all the 2s for 1s, and so on, I end up transforming this one into this one. In other words, they are 2 different labelings of essentially the same structure. Mathematically speaking, we call these 2 Steiner systems isomorphic. I can relabel one to get to the other. Let me just show you how. I've represented this version of the Steiner system in this matrix crosses in columns kind of display. And I've also done the same here for this version of the Steiner system. Now basically, if I can rearrange this one to make this one, then they are basically the same system. And here are the rules of what I'm allowed to do. I'm allowed to swap 2 columns around because that's basically just changing the order in which the blocks are presented. But remember, I'm trying to show that if I relabel the numbers of that one over there and get this one, then they are essentially the same. Relabeling the numbers corresponds to swapping the rows around. So if I can swap the rows and columns around of this matrix here and get that one, they are isomorphic. And we can see that just by swapping the rows around in this case, I can derive the other one. So that demonstrates that these 2 versions of S237 are the same, and as it turns out, S237 is unique up to isomorphism. So if you come up with a different version of S237, it is always possible to rearrange it into this one. I'm not going to go into why in this video, but it is true. But it isn't always the case. If we look at S2313 that I challenged you to derive earlier, and well done if you managed to get it, it turns out that there are actually 2 versions of this up to isomorphism. To see this, if we draw both of them up in this matrix form, you'll see that after some row and column manipulation, we can get them both looking like this. And the whole point of this is that the first part of each of these is identical. And then if you stare at this for long enough, you'll realize that you can't permute the columns any further or permute the rows any further in such a way that tries to repair the damage on the second half of these arrays to try and get them to match up without ruining the first half. So you can kind of conclude that both of these arrays necessarily have to be different. We cannot manipulate one into the other without disturbing the parts that are already the same. Now that wasn't by any means a formal proof, I just wanted to show you what it looks like when we have 2 distinct non-isomorphic systems. Now my last big question is, can I shuffle the labels of a Steiner system around in such a way that I preserve the blocks? And if so, how many ways are there of doing that? So let me show you what I mean. If I shuffle the labels of this one around, and by label I just mean the numbers, in such a way that the only 2 elements that I swap are the 1 and the 2, then this does not preserve the blocks, because originally I had 176 as a block, and now that block doesn't exist in this Steiner system. This is still a Steiner system and it's still isomorphic to this one, but what I've got is a permutation which doesn't preserve the blocks, and I'm looking for how many permutations do preserve the blocks. So let's try again. So this time I'm going to fix these three elements. I'm going to swap 1 and 3 around, and I'm going to swap 5 and 7. And you'll notice that in this case, every block is preserved. So every block that appears in here, like 176, appears here like 176, and so on. Geometrically, you can think of this as a reflection of the Fano plane. So if I pick this line here, 2, 4, 6, and flip it on that line, then I get this system here. Another one that we might have done, for example, would be to rotate the whole thing 60 degrees. That would be a permutation that preserves all of the blocks. The question is, how many ways are there of doing that? Oh boy, now we're talking. For months you've all been asking me to make a group theory video, and here we go. Asking questions like how many permutations of a structure are there that preserve certain properties or symmetries smells a lot like group theory. And we'll get there. For now, let's just calculate the number of permutations of this Steiner system that preserve the blocks, just to get a feel for things. Well, let's start up here and ask ourselves, how many different labels could I place here? Clearly there's 7 options, so I get 7 choices for the number that goes there. And now let's pick another position. How many choices do I have for the label that goes there? Well, there are 6 remaining, so I've got 6 choices. Now look at this position down here. It's actually predetermined what number I have to put there, because whichever 2 labels I put in these 2 positions, they defined a block. So the element that completes their block must go here. So for example, if I put 3 there and 2 there, well, the block 3, 2, 1 existed there, which means when I map it over here, 3, 2, 1 must exist there. So whichever 2 I pick, by definition, define a block. That's what a Steiner system is. So there is a 3rd element that completes that block. So I actually have no choices over what to put here. So I'm just going to write a 1. In other words, I have 1 choice for what element goes there. Okay, now let's pick another position. How many choices do I have for the element that goes there? Well, I've already removed 3 labels from my set of options, so there are 4 left. Okay, now in a similar way that this one was predetermined, actually everything else is predetermined. The labels that I put here and here are going to define what ends up going in there. And for example, the labels that I put here and here are going to define what label goes in there. And finally, the labels that I put in here and here define what label goes in there. So, how many choices did I actually get to make in that whole procedure? Well, these ones were predetermined, but I did get to make 7 choices here, 6 choices here, and 4 choices there. So the total number of options is going to be 7 times 6 times 4, which is 168. Now, if you don't know anything about group theory, don't worry about it, we'll get into much more detail later. But this is, in essence, what a group is. A collection of permutations that preserve the properties of some structure. And these permutations, these shufflings that preserve the blocks, are called automorphisms. All of the automorphisms together form what we call the automorphism group. So as we've seen, the automorphism group for this Steiner system contains 168 elements, and it's actually quite a special group. It's what we call a simple group. It's one of an infinite family of simple groups, and it has a name, PSL27. Or if you're a group theorist, we just call it L2 of 7. Or if you're a Lie algebras guy, you call it A1 of 7. And it's also isomorphic to L2 of 3. Yeah, it's a problem. Mathematicians, they did all the hard work categorizing all the finite simple groups, then insisted upon using confusing and non-standard notation to describe them. During my research for this video, I found this amazing entry on the Wikipedia page for classical group, under the subheading Notational Conventions, which describes nothing except a link to another page discussing notation issues. Anyway, you get the idea. Finding all of the automorphism groups of a Steiner system gives us a group. Sometimes very interesting groups, and actually the Steiner system that we're going to look at for the rest of the video has an awesome group at its heart. You may know already that all the finite simple groups have been categorized into several infinite families, and then 26 kind of leftover groups that don't really fit into any of the patterns. These are called the sporadic groups, and you may have always wondered, where do these sporadic groups come from and how did we find them? Well, you're going to become acquainted with several of those sporadic groups before we've concluded our study of this most amazing Steiner system, S5824. Okay, so compared to the ones we've looked at so far, this guy is a bit of a beast. Let omega be the set of integers from 1 to 24, and we're looking for blocks of size 8 such that every 5 set is contained in a unique block. And it's here that I'll introduce the language that we usually use to refer to these blocks. Here we call them octads. Oct meaning 8, like in octopus and octagon, October being the 8th month, or at least it was. If you're gonna add 2 more months to the calendar, put them at the end, you monsters! And all the other Greek you already know can be used to refer to these sets as well, like a tetrad is a 4 set and a dodecad is a 12 set, and so on. Using the formula we derived earlier, we can work out that this Steiner system contains 759 octads. That is quite a lot. If you want to bust out pen and paper to try and work out all the octads, be my guest. I will give you a clue that will make life a little bit easier for you. It does exist. Always helpful to know in advance. Anyway, pause the video now if you want to work it out because, spoiler alert, it looks like this. Pretty unwieldy. And now remember my Highlander question? If I give you 5 numbers from omega, can you find the unique block to which they belong? Well, that's the question we'd like to be able to answer. So let's just take 5 random numbers. Let's take, say, 4, 9, 10, 13, 21, and find the unique octad containing those numbers. Go on, I'll wait. Okay, I lied, I don't want to wait. But you can appreciate that even if we can calculate S5824, solving this problem of given 5 numbers, find the octad is still pretty difficult. Now you might be thinking, well, if I have a list of all the octads on my computer, I can just run a search. And you're right, but what you're forgetting is, that's boring. Also, what if you're a young Rob Curtis in the 1970s with much more limited computer access? Also, more importantly, and more interestingly, what if we want to find the unique octad without computing the whole system first? It's possible. We use the MOG, the Miracle Octad Generator. Here's how it works. First, we find the position of the numbers in our 5 sets in this diagram up here. I'm going to call this the number grid from now on. Now, I've been taking omega to be the set of integers from 1 to 24, but they actually take the set of integers from 0 to 23. So still 24 numbers in total, just starting from 0. But also, instead of the number 23, they use the symbol infinity. And that's fine because the choice of 24 objects is arbitrary, but why infinity? It doesn't matter for now, nor does it matter why the numbers are written in this weird order. There are reasons for all of these things, but later. So we found our numbers, and now the game is to match this instance of the number grid to one of our 35 shape grids. Now, the number grid is made up of these 3, what we call bricks, these 4x2 arrays. And each shape grid is made up of a rectangle and a square. Now, these bricks can be freely permuted, because what we're going to do is we're going to match one of these 3 bricks to the rectangle, and then the other 2 bricks we put together to match up with the square, and in some way, this will tell us how to complete the octad. I'm going to go through the whole process from start to finish, just to give you a feel for it, and then I'll explain it in more detail. Alright, let's do it. So because that middle brick contains 3 numbers, I actually know that that means the middle brick will correspond to the rectangle of one of our shape grids. And now I search across all rectangles looking for 3 squares in that arrangement all the same color. So for example, I've got a match here because 3 gray squares are all in that arrangement there. This one is also a match. This one isn't a match because I've got 2 white and 1 grey, and this one again is a match. There are actually 5 rectangles that form a match in this case. So I've simplified the diagram down to our 5 matches, and now what we do is we put the other 2 bricks together, in any order, it doesn't matter, and I look for that specific pattern in any of the squares. Again, I'm looking for 2 entries in those specific positions, both the same shape, be it a white square, grey square, dot, or circle. Here we can see that this is the only square that works, and there will only ever be 1. And now here's where the magic happens. The shapes that we used to find the grid are the shapes that we now take. So we used white squares to find the rectangle, so I take that white square there. And I use circles in the square, so I take the other 2 circles. Now we should have 8 red things shaded somewhere in our diagram. Now the final step is to bring this back to the number grid. So the middle brick I used for the rectangle. So now this tells me I need to include 1 in my set. The brick on the left I used shape left. So this tells me I need to bring 6 into our set. And the right hand brick I used for square right. So this tells me I need the 2. and including those numbers into our 5 sets completes the octad. It's so good. It's just magic. Now, let me break that down into a bit more detail because there are a few cases to consider. Case A is when we have all 5 numbers in one brick. Case 2 is when there is 4 in one brick and then 1 number elsewhere. Case C is where we have 3 in one brick and the other 2 numbers are elsewhere. And then the final case, D, where we have 2 numbers in 2 bricks and then 1 number in the last brick. Case A, all 5 numbers in one brick, is actually the easiest because in that case, the entire brick itself is just the octad. The reason for that is if I just take any rectangle where 4 of the numbers match, like this one, so these 4 grey squares match these 4 numbers, then the other number will be of a different colour, and then when I fill up those 3 of the other colour, then we just form the entire brick as we discussed. Case B, where there are 4 numbers in one brick, the brick that contains the 4 numbers will correspond to the rectangle. So for example, 0, 2, 8, 12, 17. This right-hand brick contains the 4 numbers, so this will be the rectangle. And now I search across all rectangles trying to find that specific pattern. So remember, I'm looking for that specific pattern made of all 4 of the same colour. And after searching, we realise it corresponds to this rectangle over here. And there will only be one in this case. That's because there are 8 choose 4 ways of choosing 4 numbers in one specific brick. And 8 choose 4 is 70. Now you can think of that as 35 ways and their complements. And we've got 35 distinct grids here. So every possible choice of 4 numbers in a single brick of 8 is accounted for somewhere in one of the rectangles in this diagram. Okay, and now remember we put the other 2 bricks together to form the square. I'm going to take the 0, and when I match it up with the square, I see that the 0 has covered up a grey square there, so the other 3 grey squares will give me the final 3 numbers. Pulling it back to the number grid tells me I need 5, 4, and 16. Those 3 numbers will complete the octad. Case C, where there are 3 numbers in one brick, the brick that contains the 3 numbers will be the rectangle. Let's say, for example, 6, 11, 13, 19, 20. So I start with that brick and search across all rectangles for that specific pattern. Remember, I'm looking for this arrangement of squares in the rectangle all the same colour, so this example doesn't work because there's 2 whites and 1 grey. But this pattern does work because there are 3 white squares in those positions. Again, I've just simplified the diagram down to the only 5 cases that we care about. Note that in this case, there will always be exactly 5 cases because there's 3 numbers in this brick that I'm interested in, and then there are 5 numbers that we could potentially complete it with. So they are the 5 options. Now, we've taken this middle brick for the rectangle. That means we put these 2 bricks together for the square. I'll put this one on the left and this one on the right, but it doesn't matter. From this left one, we take the 6 and the 19. And now I play matchup with the squares. So this is grey and white, that doesn't work. This one is dot and grey, that doesn't work. This one is circle and white, that doesn't work. And this one is 2 dots. That must be the one that works. There will always be exactly one. I can actually stop the process now that I've found it. I'll just prove to you that this one doesn't work either. That's a white square and a dot, so it doesn't work. So this really is exactly the one that we need. The shape that was matched were the dots, so I take the other 2 dots, and in the rectangle, the shape was the white squares rather than the grey squares, so I take the missing white square. That will tell me which numbers I need from my number grid. So from the rectangle, we took the 4, so that goes into our set. From the left part of the square, we actually took nothing else, so we just stick with the 6 and the 19. But from the right, we gained the 8 and the 10, so we stick those numbers into our 5 sets, and that completes the octad. Now, case D, where the numbers are spread 2 to 1 among the brick, is actually the trickiest one, and that's because any one of the 3 bricks could turn out to be the rectangle. So we started with the rectangle in the other cases, but we can't do that here. We actually start with the square, but first we're going to make a few observations to make the process much easier. Focus on the grey squares for the time being, but the choice of shape is arbitrary. Anything we learn about the grey squares can be applied to the white squares, dots, and circles. If you stare at it for long enough, you'll notice that either there is 1 grey square in every column, or there are 2 grey squares in 2 columns. That is true for all of them. It is never the case that there are 3 in one column and 1 elsewhere, for example, or that there are 2 in one column and then 1 in a column, 1 in a column. It's always 1 in each column or 2 in 2 columns. The only exception is this one here, where there are 4 in one column, but this one's quite special. The exact same thing is true for the rows. It's either 1 in each row or 2 in 2 rows. Never 3 and 1, never 2 and 1 and 1. Again, the only exception is this one here, where there are 4 in one row. But these two are quite special among the shape grids. Now that is actually a really helpful observation, as it helps us to narrow down the cases in the 2-2-1 spread among the brick case. So let's look at an example of that now. Let's look at the example 1, 8, 10, 19, 21. Now remember, any two of the bricks could come together to form the square, so we'll deal with each case in turn. Let's say that brick 1 and brick 2, the left and middle bricks, come together to form the square. So from brick 1, I'm going to pick up this 19 here, and then from brick 2, I'll take the 1 and the 21. This also means that brick 3 will form the rectangle, and we pick up the 10 and 8. Now this is where we can use our rows and columns rules in the square. So look at this square. We know that the rows are such that there is one symbol in every row or 2 in 2 rows. Obviously in this case, it's going to be 1 in each row. So we know that this third row needs an entry. The columns behave the same way, either 1 in each column or 2 in 2 columns. And obviously in this case, it's going to be the 2 in 2 columns case. So we can deduce that this entry is also required. Now, that's the sort of thing that you can do in your head, because as you are scanning your eye across these squares, it's easier to look, in my mind at least, for 4 symbols like this than looking for 3. After a bit of scanning, you will land on this one here. This is the only square where these 4 entries match. However, have a look at that rectangle. This one is a white square, this one is a grey square. We've reached a contradiction. So brick 1 and brick 2 cannot come together to form the square. Let's try it for brick 1 and brick 3 next. If brick 2 and brick 3 come together to form the square, we pick up the 1 and 21 from brick 2, and then from brick 3 we pick up the 10 and 8. Now we can actually rule this case out straight away, because if this corresponds to a square, it breaks the condition that the columns have to be 1 symbol per row or 2 in 2 columns. Here we've got a 2-1-1 split. Can't happen, let's throw it away. So it must be the case that it is brick 1 and brick 3 that come together to form the square. So from brick 1 we pick up 19, and from brick 3 we pick up the 10 and 8. Using the rows and columns rules, we can see that we're in the 1 symbol per column case and the 2 in 2 rows case, so we need to take this entry here. I forgot to take the entries from brick 2, so let's just quickly do that. We need the 1 and the 21. Now scan across the squares, looking for this particular checkerboard arrangement, and we see that it must be this one here, where those 4 dots are. And now notice that in this case, both of these entries are in grey squares, which is good, it's a match. So now we can colour in these 2 grey squares, and they will tell us the numbers that we need to complete the octad. And just remember, it was brick 1 and brick 3 that came together to form the square, so in brick 3 we gained the 6, in brick 3 we actually didn't gain any numbers, and then in brick 2, which was the rectangle, we gained 14 and 16. So that is the unique octad containing those 5 numbers. The 2-2-1 case is the most awkward, but I probably made that look more difficult than it really is, because I was using all these diagrams and things where usually you would just do that process mentally, ruling out cases with the rows and columns and things like that, and the more you do it, the more you develop a sense for which shapes are even possible. Indeed, some authors write that even with a little bit of practice, you can execute this entire procedure in a matter of seconds. And I believe them, but also bear in mind that we're talking about the likes of John Conway here. So when he says that he became very fast with practice, it's like, yeah, of course he did, he's John Conway. Even so, try it for yourself, it's a really fun procedure to carry out, and you will notice that your fluency quickly improves. It's just amazing that this diagram even exists. I love it. Now, during my research for this video, I discovered another amazing link between this Steiner system and a piece of mathematics called the hexacode. Understanding this gives an arguably faster way of deriving octads. But this video really is about the MOG, so I've put my findings in the extended cut of this video available to my patrons. So, very cool. And what's more, we can actually use the MOG to discover many more properties of S5824. It helps us to prove that, amazingly, S5824 is entirely unique up to isomorphism. It helps us to derive its automorphism group, which, as we said before, is one of our beloved sporadic groups, and it helps us to classify that group's maximal subgroups and so much more. But, I hear you ask, where does it come from? What is it? Why does it work? Well, now that we have a good grasp of Steiner Systems in general, we're ready to delve into S5824 in much more detail and discover how the MOG was constructed and how we can use it to derive all of those amazing properties we spoke about earlier. And that's what we'll do in the next video. Oh, don't look at me like that. Trust me, there is so much good stuff to explore here that it's better to do it in multiple parts. Also gives me some time to film and edit the next parts rather than saving it all for one 2-hour video. So, sorry to leave you on a bit of a cliffhanger, make sure you subscribe to catch the next part, and I'll see you there. Thank you so much for watching, and thanks for your patience on this one. It's currently exam season in the UK, and elsewhere in the Northern Hemisphere, I guess, and it's the most hectic time of year for teachers and tutors like myself, so I haven't had as much time and energy to work on videos. An enormous thank you to my patrons for all of your support and advice over the last few months. I love our growing nerdy community, and your support means I can dedicate much more of my time towards making videos. One day, I hope to do this full time. If you'd like to support the channel, please consider doing so on Patreon, and if watching streams is your thing, don't forget to follow me on Twitch. This has been another Proof Under Another Roof. Cheers.